Now we're getting into the theories of reactors. As we have covered in bioreactor classification, there are two major types of bioreactors based on the growth mode of the biomass: suspended growth reactors and attached growth reactors. This classification is especially important in modeling, as these two types of bioreactors have drastically different mathematical descriptions. In suspended growth reactors, the biomass is well mixed in substrate. There's no barrier for the biomass in utilizing the substrate. The substrate utilization rate or biomass growth rate only depend on the substrate concentration and biomass concentration. In attached growth reactors, the biomass is grown in biofilms, through which the substrate needs to diffuse to be utilized. So the substrate consumption rate or biomass growth rate also depends on mass transport performance of the substrate through the biofilm, in addition to the substrate and biomass concentrations. In this section, we will focus on modeling the suspended growth reactors, which is the most common reactor type to treat domestic wastewater. In this class, we'll start with the most simple setup: one aerobic CSTR treating a single soluble organic substrate using a single type of biomass. There are three types of reactor configuration models we can use. The biomass separator configuration that uses an ideal biomass separator to achieve solid-liquid separation. Similar to a polymeric membrane, the biomass separator only allows soluble component to pass through, while keeping the solids, including biomass, in the reactor. The waste stream containing solids is directly removed from the reactor and has the same characteristics as a bulk solution. The Garrett configuration has a clarifier to recycle the settled solids, including biomass, back to the reactor, but removes the waste biomass directly from the reactor. And the conventional configuration that is closest to the real-life conventional reactors. It has a clarifier after the bioreactor to settle the solids, including biomass. A part of the settled solids is recycled to the reactor, and the other part is wasted. For simplicity, the biomass separator model is used here. To model the reactor, mass balance needs to be established. But before writing the mass balance, we need to introduce the retention time. The retention time is the average time a component spends in the reactor. The hydraulic retention time, tau, is the average time liquids spend in the reactor. It is calculated as the volume divided by flow rate. The solids retention time, on the other hand, is the average time solids or biomass spend in the reactor. It is the total mass of solids in the reactor divided by the mass of solids wasted per time. In the biomass separator configuration, because the waste stream is the same as a bulk solution, so XW equals to X. SRT equals to V over FW. We'll use this expression repeatedly in the next couple of classes. Now, we got the basics covered. Let's start with the mass balance. Recall the generic form of mass balance. The accumulation rate of component A equals to its feeding rate through influent minus its vacating rate through the liquid effluent minus its wasting rate through the wasted solids plus the reaction. In the simple setup of aerobic biological treatment of one soluble substrate with one type of biomass, the component A can be substrate concentration SS, biomass concentration XBH, and debris concentration XD. We are also interested in the oxygen needed for the reaction, SO. These components can be connected by the stoichiometric relationships for growth and decay that we have covered in previous sessions. The process rates can be described with kinetics equations that we have also covered. The stoichiometry and process kinetics for the setup can be summarized with this matrix. The two rows are processes occurring in the reactor, including growth and decay. And the second to the fifth columns are the components of interests and their stoichiometric coefficients. The last column is a kinetic expression for those processes. We can use this matrix to find the reaction term in the mass balance, Ra, for each component. It is the sum of the products of stoichiometry and process rate for component A in all the processes. For example, the reaction term for biomass XBH is mu H XBH minus BH XBH. The minus sign comes from the -1 stoichiometric coefficient for the biomass in the decay process. We can do the same for the reaction term of oxygen requirement, SO. Recall that the previously shown stoichiometric equations are COD based. But for the particular matters like biomass, TSS and VSS are more commonly used. We can do a simple conversion from COD-based biomass concentration and yield to TSS and VSS-based biomass and yield, with the conversion factors IOXBT and IOXBV. Note that the yields will have a unit of gram TSS of biomass produced per gram COD of substrate consumed. Typically, IOXBT equals to 1.22 grams of COD per gram of TSS, and IOXBV equals to 1.4 gram of COD per gram of VSS. With the conversion factors, we can write the stoichiometry and kinetics matrix using TSS-based parameters like YHT and XBHT, and the TSS to COD conversion factor IOXBT. The usage of this matrix stays the same as the one using COD-based parameters. Of course, in reality, the models are much more complicated. There are multiple substrates and biomass groups in multiple processes. There can also be cross-feedings and inhibitions. This is one example matrix from the activated sludge model 1.